Okay, my name is Herdian, and I come from Taiwan. It takes like 28 hours, and I still pretty jet lagged right now. So the idea is that when I joined this challenge, is that our previous works heavily data driven. We use a lot of algorithms, but this time I personally want to use another approach, completely different approach. So we just want to use a simple algorithms, but now we simply just doing one thing, which is correcting collider precision bias, and see whether it's going to survive against other competitors that I will guess that it will be heavily data driven. We'll use like complex algorithms. So the idea is that we want to use the epigenetic clock to assess a disease mechanism. But the problem is actually what we're trying to do right now. We try to predict a gestational age in the context. It's actually a result of decision making of clinicians. And it usually we collect the samples because the pregnancy terminated due to medical conditions, and not exactly that we just arbitrarily sample the placenta. And except perhaps for chorionic villus sampling, but even for CVS, there's some medical indication for that. So it's not quite really random. And the previous placental epigenetic clocks were claimed to be robust, and they claimed that because of three reasons. First, samples included complicated pregnancies. The second reason is that because when they use normal placental clock, they claim accurately predict gestational age even in complicated pregnancies. And then the third reason is that the correlation remain after they adjust for preeclampsia. However, we argue that for the first reasons, in our opinion, is simply including the complicated pregnancy will not solve the problem, because particularly the selection bias will result in the generalization problem. For the second reason, it's actually also arguable because as you see here, that in the earlier pregnancy, in the preterm pregnancy, it's pretty much biased. And for the third reason is that preeclampsia is not the only one that's gonna lead to pregnancy termination. So we argue only adjust for this condition is not enough. So there's other conditions. And as you can see that other condition is very likely to lead to the preterm deliveries. And that's why in our arguments that it is less precise in earlier trimester. So it's already explained about the challenge. And we just do, I would say, a standard pipeline for data preprocessing. So we try to refrain ourselves because I would say at the first time we just want to test whether correcting collider restriction bias will work. But in the process, because we see the leaderboard, there's some ego play here. I'm not going to list this. So there's we tempted to use like a many approach, but we try to refrain that because we want to focus on the collider restriction bias correction. So we just use this standard data preprocessing, and then but the organizer actually didn't provide the phenotype data for obvious reason, because if you collect like several data sets from different studies, they have like an inconsistent phenotype availability. So, but in our framework, we need that. So we try to trace back from the GSE numbers what kind of phenotype data they have, and then we see which kind of condition that actually relevant that may lead to the pregnancy termination. And to solve the availability problem, we just use a simple imputation method. Of course, the imputation accuracy will be very deep, very widely in accuracy, but our goal is to see whether this additional information will help or not in the increasing the precision. So we use structural causal modeling just to find out how we're gonna arrange the model, because we will use a multi-stage prediction model. So we use many models in one model. So we combine that, and to design that, we use this causal graph to find out whether it is can be recovered or not from the selection bias. So the idea is that in here, what we try to predict is we use this methylation to predict this biological age, but it's not exactly the biological age, because it's actually the stational age at sample collection. So every medical condition that leads to termination will very likely to end up as the sample of the training data. So we can see here, if you know about the structural causal modeling, there is a path between the sample collection process with the placental clock. So our training data only include, most of the data set usually collected using case control, which is probably there are some of the controls that not included, like normal placenta, that actually not represented in this data set. So what we want to do, we want to recover to estimate of y to be at least like approximate to the estimate of y not given to the s equal 1. And the way we do that is actually to block the paths, which is the medical condition that leads to pregnancy termination, or as an indication of CVS. So the problem is not all selection bias recoverable. So we use this from the Barenboim, Tian, and Pearl. There's some of the selection bias that actually can recover. So if we identify our graph, we can see here that it is recoverable. Well, of course, we cannot completely recover that, because some condition, for example, like placental abruption, we don't have the phenotype data, but it might also lead to the pregnancy termination. But at least we can improve as much as possible. We can collect the phenotype data. And then there's two kind of features here. The first feature is the beta values of the CPGs, and the second feature is the phenotypes. And we just, again, only use the standard pipeline for this. But I think the difference with the other participants is that we use the phenotype data. And we simply use a correlation matrix to know whether which type of phenotypes is correlated with the gestational age. And we only use that phenotypes to be included in our model. So our model is actually multi-stage. So the first stage is we only use normal placental clocks, because the long-term goal of this placental clock is we want to study the aging mechanism. So first, we want to know which CPGs actually contribute to the normal aging. But if we use this model to any kind of samples, like there is a complicated pregnancy, then of course there's some residuals in this complicated pregnancy. And then we build other models to predict the residuals. So instead of including all of them, so in the first model, we only include the normal one, and then we use this model to all samples that also include abnormal ones. And so we get the residuals, and then we try to predict the residual using different way. The first one, because we impute the phenotype data, so we have predictive probability of each medical condition. So we simply use that. So we try to do the simple approach first. And just for disclosure, this step, we plan only this step, before we submit our first model to the leaderboard. So for the next step, we design that based on the feedback what we see in the leaderboard. I think this is like inevitable anyway. Psychologically, information in the leaderboard will drive us to, I would say, we are the human algorithm that's gonna somewhat gonna overfit our model according to the leaderboard, right? The second model, we use predictive probabilities. So you can consider the second one is actually somewhat like a multiple imputation, because in the first one, we only use complete data. For the second one, we use all of the data after imputed, and then we again have the model. So we have one model for each medical condition. We have 13 medical conditions, so we have 13 models to be stacked in one multi-stage model. And then the third part, we use a clinical knowledge to see competing risks. For example, if a sample have higher probability to get a miscarriage, it's very unlikely to get a preeclampsia, for example, because preeclampsia, it happens at the later gestational age. So we just use something kind of rule of that. And we only use two algorithm, elastic regression and random forest. But at this next step, we only use elastic regression because we see that random forest pretty good. Like in our training data, when it goes to the leaderboard, it seems like the other way around. And so this is the method that we develop after we evaluate the result in the leaderboard for the first step. So this is the first one, and as you can see that actually in our data, the best one is actually this, the clear cut. Oh, I lost it. Oh. Yeah, I cannot. Yeah, but in the leaderboard, it's the opposite. So in here that we see that although we hypothesize that medical condition probably helpful, but we only use the predicted probabilities to correct the residual, to predict the residuals. It's probably not enough. So in the next step, we consider to use the beta values. So basically, we have the residual models for one for each the medical condition. So we use the beta values to predict gestational age only to sample with that medical condition. So for example, we have 1,000, all the sample 1,000, but only 100 for preeclampsia. We only use that 100 that only have preeclampsia and try to predict the gestational age. So the idea is we try to predict gestational age. We hypothesize that every medical condition will have different trajectories of gestational age. And that for the next model. And then, so for this one, I lost the pointer. Oh, oh yeah, I get it. Yeah, I get it, sorry. So for this one, we only use beta values to predict the residual. And for this one, we have one model of gestational age for each medical condition. And then we multiply that with the probability. So because the probability of getting, for example, preeclampsia or like a FGR will be very differently for each patient. So we try to multiply each probability with the gestational age predicted for the model for that condition only. And then we then sum like average the gestational age. So it's like more like a weighted average, but weighted by the predicted probabilities. And then we also combine that after we use that every condition gestational age, we also again predict the next residual, the subsequent residuals with only the CPGs, because we understand that we don't have all of the medical condition. But first, we need to find out which part of the residuals is actually explained by these medical conditions. Because if we do exactly the opposite order, so we try to use the CPG first, and then we try to correct the residuals using the condition, it's actually felt miserably. So somehow just simply have a different order of this stacking model, it results differently. So the last one with combination is actually the best one. As you can see here, this blue one. So we use only the CPGs. We don't use the medical condition. It's actually better than if we use the medical condition probability to predict the gestational age. But when we multiply the probability with the predicted conditional age for each medical condition, and then we sum up that, we have a far better here. And then if we combine again, we again predict the subsequent residual, we have a better one. So finally, we end up with choosing the ResCom GA model for that, the combination one. But we still lose with this model from Orsolio PPAC. So I actually try to find out the list of the publication of this person and to try to guess which kind of approach, just to give you a sense how this challenge actually works outside of the paper they're going to write. You only know from these presentations. And I saw that the way I just guessing, the way they develop the model is actually somewhat like retraining the model. So using like the same, for example, the current placental clock waves, and then retrain that using a new data. And so I think at that time, actually my ego, I don't want to lose this. I try to want to improve again. What could we do to improve this model? But when we try to explore that, there's no way in a way that have a reasonable in clinical explanation is gonna work better. We also can have like a mini algorithm, this and that, and probably we have a better prediction result in the leaderboard, but it doesn't necessarily will generalize, right? So we try to refrain ourselves. But the idea is if the approach of this, the top performer will be like retraining the model, it is very likely there's a chance that our model will work better in the test set. So we try to hold that and let's see if it's gonna work. But we have a confidence of that. So this should give you a sense how medical condition, how if you consider the phenotype data, how gonna help the modeling strategy. So we just try to do some comparison here. For example, this one. So in these four models, we multiply the probability of a condition with the gestational age prediction for that condition. For the first one, we have the lowest RMSE, we don't use the predicted probability. Instead, we use only the answer. So it is just for comparison purpose, because if we have the true answer, we have more confidence that the predicted probability actually the best one because it's true answer, right? So for the second one, and for the last one, is actually we don't use the probability at all. So you can see here has a different degree of confidence of the predicted probability. The first one is the true answer, and the last one we don't use at all the probability. And you can see this is training data. I don't have access to the leaderboard and test data. And you can see here that it's getting better. And I would like to know if it's actually replicated too in the tested data, because that's important. Why? Because if it works that way, then people can improve this model simply by improving the prediction models of the condition itself. So we can still improve this. Okay, I think I'm just going to skip this. It's just too much. But I think the second culprit is about how we evaluate the model. We talk about the algorithm, the modeling pipeline, but how many methods actually we develop for evaluating the models? I think somehow even like external validation, it doesn't really guarantee whether your model works well in the real world. Even if it works well now, but probably not later. So the goal is we just try to subgroups as many as subgroups. And a good thing about this challenge is if in this challenge we have an ideas of what is the benchmark RMSE we need to beat, we need to defeat. So we use the top performer RMSE as a cutoff. If you see the green one, then our model win. If you see the red one, then our model lose. And for each subgroups, you can see that normal placenta lost in many subgroups, including if we subgroup using only the dataset ID. And then if we use only the CPGs without the medical condition probability, it's getting better if we predict that. But there's some problem here, which is the triploid. It is like chromosomal abnormalities. We don't show all the models here, but most of the model, except for these two models, cannot solve this problem. So this is a subset of data that cannot be predicted easily. And when we use the medical conditions, so we multiply the probabilities with the gestational age for that condition, we do better. We can solve the problem here for the first time. But we still have a problem, like some data set is still lost here. So I predict that probably the test set will be not going well if we just use this one. So we combine that and we can solve almost all of the problem. And as predicted, that it also works well in the test set, in the independent test set data. And just to be honest, that because it's a challenge to give you a sense how participants in the participant side, how we enroll in this challenge. Anyway, we have a primary project in our lab, obviously, and then when we join this challenge, it's very likely to be a side project. I honestly just do this over the weekend because I don't want to use the working hour for a side project, and then we run out of time, and we don't have time to complete all the models for the 8050K, but we only use the 450K. But it's also get better than other models that also use 850K. So it's the enough result. I think that's it. And I thank for the Placental Cock Challenge organizer and also National Science and Technology in Taiwan that funded our postdoc work. Okay, thank you.
Test the 850, but that was before the deadline. But in the meanwhile, did you get the results, or are they still running?
Well, actually, there is some results. We actually done some models, and if you see here, when we use 850K, just to give you context, in 850Ks, the values for the CPGs that exclusively for 850Ks is actually imputed. So we have a concern, probably this imputation quality will affect that. And as you can see, even like we use the medical condition probability, it doesn't really work well.
So the good thing is that, you can build that model and then submit it to the safe Docker repository, and then we'll be able to test it. So that's good news. So we have
First of all, really great talk. Thank you. I just had a question about an aspect of the model I was really interested in. So can you discuss a bit more about how you accounted for competing risks and the fact that, the presence or probability of one phenotype can preclude or augment the probability of another?
What do you mean about the probability?
When you were discussing how, for example, if individual was at high risk for preeclampsia, then some of the other phenotypes you have in the list, for example, like early term pregnancy would be less likely. Can you discuss how you accounted for that in your data selection augmentation in the model itself?
Yeah, we actually don't use all of the phenotypes. We only use phenotype that leads to pregnancy termination. Yes, so we actually have an access. We also actually have another phenotype, for example, like fetal sex and also like many things like something like that. But also like, for example, smoking. So mother smoking also affect like a preeclampsia, but we don't use that because in our model, we don't consider that going to lead to pregnancy termination. If we have more time, we probably want to compare that too.
But just to clarify, so if you have a possible risk for preterm birth due to spontaneous labor, preterm birth due to preeclampsia, for example, you just take the maximum probability outcome, and you take the model for that condition, not to discount the risk for the other condition, right?
Yeah, I use all of the predicted probabilities.
Also, okay, so you take all
Yes.
the probabilities and you
Yes.
divide the estimates.
Yes. So it's considered like a parallel universe. What if this mother will have how many chances exactly gonna have like a preeclampsia? For example, 50%. How about this carriers perhaps like a 20%? So we simply multiply that probability. For example, if this mother is considered preeclampsia and the gestational age, for example, like 5 weeks earlier, and then this miscarriage will be like 15 weeks earlier, something like that, it will have a different wave according to the predicted probability. Yeah. So that's why the best model, this kind of model, we name that sliding doors. If you know the movie Sliding Doors, it's all about this kind of decision parallel universe, something like that.
Thank you. So we'll invite the